We're back to our usual schedule. We have an assignment due in a couple of days. And I think that's basically it. I owe you a study guide by the end of the week, but that's a ways out still. So next exam coming in a little under 2 weeks. Not quite to the halfway point between exams, but they fly because this is a quarter system where we go over so much material so quickly that if I had fewer than 4 exams in this class, there'd be so much on the study guide that I wouldn't want to give it to you. Questions before diving back in to talking about the universal language and getting into what the limits of Turing machine's computability are? All right. At the end of last time's very mini class, we were talking about the universal language and why the universal language is recursively enumerable. So we found a way to simulate this concept of outputting machine string pairs where the machine accepts the string. We needed the ability to reprogram a Turing machine to be able to recognize and emulate another Turing machine and determine whether that other Turing machine accepted a particular input string. And from the process that is currently on the slide, we can see that we are able to fully do that. So we were able to show that it is recursively enumerable. The next thing we wanted to show is that this language is not recursive, that there exists some strings that a Turing machine that we're emulating won't be able to accept in a finite amount of time. The book goes through this as a proof by contradiction. I like to think of it intuitively. It's just if you feed this universal Turing machine a Turing machine string where that Turing machine goes into an infinite loop on that string, then obviously the universal Turing machine won't be able to halt either. So we need to apply the same rules and the same logic that we did to enumerating recursively enumerable languages to this in order for it to be able to work. So proof by contradiction, if this were recursive, there would exist a Turing machine that accepts, we could say, the complement of the universal language. So we know that if a language is recursive, that means we can both accept or reject in a finite amount of time. If we look at the complement of that, we would be flipping the acceptance and rejection. We can do both in a finite amount of time. If we look at the complement, we should be able to still do both in a finite amount of time. On the other hand, if it's recursively enumerable and not recursive, that means we can accept in a finite amount of time, but rejection may take forever. Look at the complement of that, and now acceptance may take forever. And so the complement isn't necessarily even recursively enumerable. It may be outside of the bounds of what is recursively enumerable. So we'll make that assumption that there exists a Turing machine that can accept the complement of the universal language. So we can transform M into M prime, that we're going to go into the diagonalization language in a second. That is basically what we have. We've kind of seen this at this point, but we'll go back into it. We have the next slide, we'll talk about the diagonalization language. Here we, though, say the new Turing machine transforms its input into a pair that is just the same string 2 times. And we'll simulate M on WW, assuming the first W is an encoding of some Turing machine, M sub I. Second W is an encoding of a binary string, W sub I. The conclusion here is that M will accept the complement. Since we know that it accepts the complement, it'll accept WW if and only if M sub I does not accept W sub I. And if we assume that this is the diagonalization language, M prime accepts W if and only if it's in the diagonalization language, we will soon show that there is no Turing machine that recognizes the diagonalization language, And from there, we can show that it's not recursive. And this proof type is one that we will see a lot when we get into computability theory, which is the next thing we're going to be talking about, probably starting tomorrow. And we will see a lot of proofs that look like this as a way of showing computability. So this is the outline of the proof, but in order to really make it click, we need to see this diagonalization language to be able to make that work. So that, we're going to say all of these strings here, W1 up to on forever, are an enumeration of all binary strings. We've talked about that the enumeration of all binary strings is something that we can do. We just have all binary strings of length 0, of length 1, of length 2, of length 3, etc. Then we have an enumeration of all Turing machines. So the diagonalization language is just one that says, let's not try to run every machine on every string. Let's just run the ith machine on the ith string. That's it. No more complicated than that. So the theorem that we're trying to show by contradiction here is that this is not recursively enumerable. So to show this, we would say by contradiction, we're going to assume that it is recursively enumerable, and the diagonalization language is the language of some Turing machine that would accept it. So what happens when machine I looks at input string wi? If m sub I accepts w sub I, then by definition, it can't be in the diagonalization language. So remember that the definition of the diagonalization language in bullet point 3 there is wi such that wi is not in the language of machine I. So we're only trying to accept those for which the ith string is not in the language of the machine. We're trying to find that language. But if m sub I accepts w sub I, then w sub I is not in the diagonalization language. If m sub I does not accept w sub I, then by definition it is in the diagonalization language. So w sub I can neither be in the diagonalization language nor not in the diagonalization language. And from this, we end up with the contradiction that this language can be accepted. And this basically comes to the point that if this spins in an infinite sense, that, I don't know, to me, this is very mathy. The intuition behind it is that if we assume that we have a machine that accepts this regardless, what happens when this machine goes into an infinite loop? There is no way that we could recognize that. I can guarantee you this won't show up on a homework or on an exam. It's for context, I guess would be the right way to say that. Any questions on this proof type? The type will come back in an easier form. I think we'll drive this in a bit better, but I do want to handle any questions you have about why this is a path to show that the universal language is not recursive, I think is the main takeaway. All right. In case you're not fed up enough with different grammar types, there's a last one to show us. So I think when I introduced context-free grammars a long time ago, I said, this is removing all the restrictions of regular languages. It's a non-restricted grammar type. And it turns out that I was lying to you because I didn't want you to think about this at that point. But this is not technically true. What restriction do we have on context-free grammars?
One non-terminal on the left side?
Yeah, there's only a single non-terminal on the left-hand side of a production. you can imagine being able to map context to that. Basically, what context-free means is that we're not going to worry about the context in which the left-hand side non-terminal appears. We just care about when we see that left-hand non-terminal, we can expand it in any of the ways that are defined by the right-hand side of a production. However, we could have multiple symbols on the left-hand side of a production. That is something that is a restriction that we could allow for. It's not something that I would suggest because it creates a major headache, but it could be that such a grammar could exist, where we could either have multiple terminals or multiple non-terminals or combinations thereof on the left-hand side of a production. And we would be replacing the entirety of the left-hand side with the entirety of the right-hand side. Let's take a second and think about what would happen if we did that. So now restrictions are gone. Any number of terminals or non-terminals are legal on the left-hand side or right-hand side of any production. We will say there has to be at least one terminal or non-terminal on the left-hand side. We can't have lambda arrow something. That would not work for anything. So lambda not allowed on the left-hand side of the production. The question that I want to query people's intuition for is how powerful is an unrestricted grammar? Let's start with more, same, or less powerful than context-free grammars. Who thinks they are more powerful than context-free grammars? Similarly powerful to context-free grammars? Less powerful than context-free grammars? Split between more and the same? Turns out the answer is more. We get a lot more power from relaxing these restrictions when we don't have to worry about the associated context. I can absolutely see where you might be coming from with a vote for the same. The next language class that we know of are the recursive languages, where a Turing machine could both accept or reject in a finite amount of time. What do we think? Unrestricted grammars, more, same, or less powerful than recursive languages? Think about that for a little bit, and then we'll take a quick vote. Anyone want to say more powerful than recursive languages? Similarly powerful to recursive languages? Less powerful than recursive languages? This is the first question where I feel like all three of these answers could be similarly viable. Like to be less powerful is like, this was an interesting class between these two languages. The correct answer was more powerful than recursive languages. It turns out that we can write a grammar for languages that can be accepted but not rejected. So it is more powerful than that. Recursively enumerable languages, this is where we stop. It is the exact same language class as recursively enumerable, meaning that we can force infinite loops on rejection. Unrestricted grammars and Turing machines and algorithms that we can write all have the same power, which is really cool. Any questions on that in theory before we go into a little bit more detail and get an example? I'm actually going to have you try to make an unrestricted grammar, and we will see that they are very difficult to write, even for seemingly simple languages. So let's try to map these together. The procedure that we used for recursively enumerable languages is that we had that kind of diagonalization-based approach. We were going to try the first move on a Turing machine on the first string, then the first move on a second Turing machine string, then go back to the second move on the first, then make a third, and diagonally go through that two-dimensional space. But let's start with the start non-terminal of an unrestricted grammar. We do need somewhere to start. So the very first production will have a single start non-terminal on the left-hand side. Then we would find all strings that can be derived from that start state within a single step. So if that start non-terminal arrow had 17 different right-hand sides that we could replace that start non-terminal with, we would keep track of that set. We would have 17 running processes non-deterministically of here are all of the replacements that we could do from there. Then from each of those 17 steps, we could see how far could we go in a single step from there. That should be finite, not final. So there are a finite number of productions, the list will be finite, which makes sense. We can't have an unrestricted grammar with an infinite number of productions. That makes no sense. So from there, we look at everything that can be derived from the start state within 2 steps and continue this process for an arbitrary number of steps. And note that this process will never terminate. There will be recursion that gets us back to a point where we've been before, but we're still continuously adding strings to the language as we continue to do this. After we've looked at 16,405 steps, there may be new strings that are added to our language in the next step as we look at all possibilities from there. So yeah, the process doesn't terminate, but it continues to produce new strings that we add to the language. So it's recursively enumerable because if you ask the question, is this string in the language? If the answer is yes, then there is a finite amount of time before this process adds it to the language. And you can verify, sure enough, it's in the language. But if the answer is no, it's not in the language, then this process will never terminate to the point where we know that that list is complete. So it's always ambiguous between have we just not added it to the language yet, or will we never add it to the language? With that idea, we can map that directly onto the concept of a Turing machine. That's exactly how a Turing machine would handle doing this process. We could define a process to take on an unrestricted grammar on the tape and come up with a language from that, an ever-expanding language of strings that we could show are in that language. Converse, not as easy to show. We want to be able to show something like, we can't do the complement of this. We want to, given a Turing machine, derive an unrestricted grammar that accepts that language. How in the world could we do that? There's a very long proof of that we are not going to go over because it's long and complicated and doesn't do a ton for us, but it is possible. It's just not fun. So those are unrestricted grammars. The last subset of those that are interesting are called context-sensitive grammars. There are actually quite a few classes of grammars between context-free grammars and these unrestricted grammars, but it turns out that most of them don't do anything for us. They don't allow us to map onto an interesting class of languages or a class of languages that does something that is useful to us. But there is one class that is studied because it produces the same class of languages as when we talked about linear bounded automata, the idea of we can't occupy more of the input tape than the actual input size. So rules for context-sensitive grammars. So just like with unrestricted grammars, we're going to get rid of the one non-terminal only on the left-hand side will allow any number of terminals or non-terminals on both the left and right-hand side of the production, as long as, this is the interesting condition, the number of terminals and non-terminals on the left-hand side of a production must be less than or equal to the number of terminals and non-terminals on the right-hand side. So it is only ever expanding in terms of the number of terminals plus non-terminals with every single step. Why is that an interesting restriction? What it means is that we can eventually say no. When the query string that we're trying to ask, when we get something that is larger and longer than that, if we can factor lambda out as much of this, then we could start to say no. There's no further way to derive this because every other production would be increasing the size of this. So length of successive string forms only increases. And then there is a normal form, just like we've seen with normal forms in context-free languages, where we can now say this, let's fully reveal, we have a left-hand side, a non-terminal, and a right-hand side. Arrow, that same left-hand side and right-hand side, but the form A arrow B can only occur when A appears in the context between the beginning and the end. So that's why we call this context sensitive. The normal form here says that the change between the left-hand side and the right-hand side depends on its context. And only when both sides of that context are met can this rule be allowed. Here's where I want to give you an example. How are we doing so far? Any questions on this? So we start by saying we cannot generate the empty string. That's okay. Let's start with A to the n, B to the n, C to the n. We know that this language is recursive. We showed that it's not context-free and it is recursive. So it's somewhere in that boundary between context-free and recursive. And we know that linear bounded automata are also somewhere between context-free and recursive. So now instead of saying that this language is not context-free, let's show that it is context-sensitive. So I will note that simple languages often have very complicated context-sensitive grammars, but let's give this a shot. Now, any left-hand side is okay, as long as you are successively increasing or keeping the same the left-hand side to right-hand side. So you can't make something of size 3, arrow something of size 2. You can do something of size 2, arrow something of size 2, or something of size 2, arrow something of size 3. Let's give this a shot for a little bit. This is very challenging to do, so I don't necessarily expect that many people will come up with this. But play around with these and work together. You may want to work together on this. This is a challenge. Do you have any insights about getting started? Maybe I can help some people with some ideas. The main idea of this is going to be a recursive procedure. Think of it kind of like a loop, in that when you reset and get back to a particular position, what you have done is you've added an A and a B and a C to what currently exists. So we start with just our start non-terminal. We need to be able to produce a single A and B and C, or have the ability to produce, have something in the middle of that that is eventually going to produce another A and B and C via a repetition of some sequence. The other hint that I will give you is that you can do things like flip the positions of terminals and non-terminals while keeping the same number of symbols active. So if I have a terminal coming before a non-terminal, I can make that the left-hand side, and the right-hand side is flipping that. So you can move non-terminals around within your grammar to be able to place, there is something to add here in different places in your grammar. Anyone want to talk through what they've tried? What has your approach type been? from my perspective, if I'm trying this, given what we know so far in this class, my thought is it'd be really nice if we could do something like determine this A, B, C. I want something that goes after that, something that goes after that, something that goes after that, that can produce an extra A and B and C at the same time. And the issue with this is that we need to terminate all three of these non-terminals at the same time. They need communication between each other to be able to agree on when to terminate. Because if you could have an A that produces something like an A or terminate, but we can't straight terminate, so maybe we do something like this, then we would want all three of these non-terminals to pick this production at the same time. And there's no easy way to get them to cross-communicate. So this approach ends up not really working. What we need a way of doing is defining a process where a single non-terminal is going to be moving throughout this string, and we only allow termination when we get back to the front or to the rear, depending on how you want it to terminate. And one pass through this string is going to produce an extra A and a B and a C. And we need the ability to move this non-terminal back and forth. You want some more time to work? You want to see a solution? All right, let's explain a solution.
Okay.
This is going to look a little strange. But let's walk through this. So here was that production that I showed early on. We're going to have S arrow and be able to produce the original ABC and just terminate, because there's no other way to do that. If we go down this right-hand side, we're going to be producing at least one more A and B and C. The only place that this entire process can terminate is down at the very end. So there's at least one non-terminal in every other production, which means that we're going to be going through a sequence of actions that's going to produce an extra A and B and C. If we're done after a single A and B and C, we'll take this production if we're going to go through another production, another loop to produce an extra A and B and C or more than one, then we'll pick this production. So let's start with the S arrow A, capital A, B, C. What we're going to be looking for within this is we first are going to move this A to produce an extra B and C at the rear of this. And the way we're going to do this is we need to swap the position of the AB to move the A in between the B and the C. So that's what the second production here is doing. We're going to take the AB and just flip the order of the terminal and non-terminal. So that creates a B, capital A, C in our string so far by making that flip. When we do this, we can recognize the context of the A being between the A's and the C's by if we had just flipped this and then it's between that and a C, then we're able to recognize we're now between the A's and the C's. So there's the context that this left-hand side represents. When we do this, we're going to replace the entirety of the A and the C with a B, B, C, C. Let's see what that looks like. So we're going to take this chunk and replace it with the right-hand side. So we still have the A and the B, but now we have a capital B, B, C, C. So the A recognizes that we are moving right through the string. The capital B, we are moving left through the string. So when we recognize we are between the B's and the C's, the goal is to add an extra B and C, which is exactly what we have done. If we took out this B at this point, we've made the extra B and the extra C. We now just need to add the extra A in order to reach the next iteration of A, B, B, C, C. So to do that, we're going to recognize this ordering, the B, capital B, so that we can move the non-terminal back through all of the B's. So this will move that to the point where when we reach this left-hand side, A capital B, we know that we are now between the A's and the B's, which is where we can add our extra A. If we are done at this point, we can choose to replace this A with two A's, which adds a single A, or we can add a single A and repeat the process. And since we're still between the A's and the B's, we can recurse to this point where we can then add another A and B and C. So let's go through that one more time just to show. I'll see that on one hand, we could turn this into A, B, B, C, C, and be done. Or on the other hand, we could turn this into an A, capital A, B, B, C, C. And if that's the case, we're adding at least one more. One more path through this, we recognize that we see an A followed by a lowercase b, so we're going to be doing that replace. So we have A, we still have our AA, but we're taking the A capital B and turning this into a B capital A. And we still have our last B, C, C. We still have that AB subset from this, so we're going to recurse and do this an extra time. Let's just make sure that the A is all the way past all of the B's. So we have A, B, B, capital A, C, C. And now we're at the position where we see the AC. This tells us that we are done, we've terminated, we've moved past all of the B's, and we're ready to, since we're between the B's and the C's now, we can add the extra B and C. We have our A, B, B, our AC becomes a capital B, B, C, C, with an extra C on the end. From here. So now we have three B's and three C's. We just need to go back and add the last A. So we'll recognize that this B can move backwards because of the BB. From the second to last one there, we'll move it backwards. We have A, B, capital B, B, P, C, C, C. And one more time, this B can move back past the B's, second to last production. A, capital B, 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 C, C, C. And now we're at the A capital B. So we can add an extra A here and terminate, like we did here, where we get A, B, 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 C, C, C. Or we could go on and do even more work from here. I'm hoping that the recursive process here has become a little bit more straightforward. We can see exactly how and why this is doing it. This is complicated. I don't expect people to be able to come up with this given the limited amount of time that we have. But it's pretty cool, but also recognize there's quite a bit of complication there for a relatively simple language. All we're doing is scanning back and forth between a string, but how that grammar comes to be is there's quite a bit to that. Questions on any of this derivation? Why this grammar matches that language? How this is context sensitive?
We could do the same thing except maybe right to left as well, right?
Yeah.
Okay.
Yeah, you terminate when you get to the end instead of at the beginning and recognize you're in a particular position. Yeah. I don't know. I find this really cool. Kind of mind-bending, but it does work. That's pretty much what I just wrote out. But I think seeing it derived helps to understand why it maps to grammar. So there's a derivation. We could keep going though and make a to the fourth, b to the fourth, c to the fourth, etc. We can show that context-sensitive languages are also recursive, just like we showed that linear bounded automata are also recursive. But it turns out that they're not the same. Just like linear bounded automata were restricted from recursive Turing machines or recursive languages, then we can also show that context-sensitive languages are beneath the recursive language structure. Also shows that recursive languages are not context-sensitive. So that's pretty cool. The end of this slide deck is going to show us the Chomsky hierarchy, which is a way of visualizing a lot of what we have seen throughout this course. So here are all of the language classes. Here are a lot of the language classes that we've seen so far. At the very center, we have our regular languages, which are a subset of the deterministic context-free languages, those for which we could construct a deterministic pushdown automata. And those are a subset of the context-free languages, the class of language for which we could construct a non-deterministic pushdown automata. Then outside of that, we have our context-sensitive languages. Outside of that, we have our recursive languages. And outside of that, we have our recursively enumerable languages. And even outside of that is the big box that is all of the languages, including those that are not recursively enumerable. So there are languages that are outside of the scope of this entire hierarchy, but it shows all of them are subsets of each other throughout this. So every regular language is also context sensitive. Every context-free language is also recursively enumerable, etc. Anything that is a smaller circle in the middle is also part of the class of languages that has some circle that's outside of it. The other few language classes that we've seen are linear. And so where do the linear languages fit within the scope of this? So we have regular, deterministic, context-free, and context-free that are all part of the other Chomsky hierarchy, but linear languages fit in that there are all regular languages are linear, but there is not necessarily perfect overlap between deterministic, context-free, and linear, but both of those classes of languages are context-free. So between these two diagrams, we have every major language class that we have talked about throughout the entire quarter, which is awesome to see in one big diagram of here are the classes of languages, their associated power. Any questions on this? I usually get a couple of how does something that we've related to or talked to fit into this visual of everything that we've seen? Anything I can clarify? You're welcome to keep thinking of a question while I get the next thing up. We're basically out of time, so I'm only going to be able to motivate it. We're going to start talking about the actual limits of algorithmic computations. We've set that up now with talking about recursive languages, which are algorithms that will terminate. We have recursively enumerable languages that will terminate if we accept. But what does this mean with regards to the limits of the power of a Turing machine? What can't we do with a Turing machine? Given infinite compute power, what could we not answer? What kinds of questions are there out there that are just beyond the scope of the modern computer? So, talked about what Turing machines are capable of, but we're going to dive into what Turing machines are not capable of. And as we get better and better technology, all we're doing is getting closer and closer to being able to have our modern computer be able to do what, in theory, a Turing machine can do. But that is the limit of what the modern computer can do. Even if we had infinite RAM and the fastest algorithms that could make time complexity irrelevant, basically. If it's something that we could solve, then we could do it close to instantly. That is the optimistic view of the future computer. But there would still be some things that computer could not do. So, any guesses? What could a computer not do? I'm going to leave that for you to have nightmares over between today and tomorrow. Tomorrow, we're going to introduce the concept. I don't even know if I want to say it. The halting problem. So the halting problem is something that a computer can't do. So we're going to introduce that, and it will be our video day, because this is something that I will explain, and a Veritasium video does a much better job than I could with advanced graphics that I can't reproduce in a short period of time with just a whiteboard. But it leads into a bigger discussion of the limits of math. What can't math do? And that's something that has been discussed, argued about voraciously over the last 100 years. So that is the contents of that video. So make sure not to miss tomorrow. It's really cool. And we'll have a discussion about it after it finishes. Office hour starting now for any homework assistance.